Hello everybody, welcome to this lesson on correlation and cleaning data. So, two topics from the stats section of the course we're looking at today. We'll get all of correlation done. We might not get all of cleaning data done. We might go onto some of that in the next lesson. So, just a little bit of admin to start off with then. This work is going to be submitted as part of week 26. If you go to the course page, you can see everything there. The work that's due in on Thursday, that's all the week 25 stuff. So if you've not done that, that's what's got the deadline of Thursday. And then all of the stuff from this lecture and the next lecture, they don't need handing in until the week after. Okay, let's get started then. So in today's lesson, these are the things we're going to be looking at. A lot of this stuff you may have met at GCSE and it'll just be a recap, and then we'll be building on that with some of the new stuff that you'll be learning today. So we need to be able to describe the relationship and correlation between two variables. That's something you should hopefully be familiar with from GCSE. Something that may be new to you is we're going to be looking at interpreting values of the product moment correlation coefficient. And we're also going to be looking at understanding that correlation does not imply causality, something you might have seen before. And we're going to be looking at interpreting the gradient and intercept of a regression line. So maybe some stuff you've seen before and a bit of new stuff. Okay, so a definition that you should hopefully be familiar with already is that correlation describes the strength and type of relationship between two variables. And also that if you've got a data set that's got two variables, we call that bivariate data. So, a couple of definitions we're going to start off with then. We need to be talking about positive and negative correlation and also the strength of the correlation. So we're only going to use strong or weak. So positive correlation means that if we were to draw a line of best fit, it would have a positive gradient. The closer the points are to the line of best fit, the stronger that correlation is. So this diagram is a typical example of strong correlation and weak correlation. We could have no correlation if there's no relationship between one variable and the other. Or we could have negative correlation where if you were to draw a line of best fit, it would have a negative gradient. And again, we can have strong or weak correlation. So, just want you to have a think to yourself for a second how you'd answer this question. The main purpose of it is to make sure you can understand the difference when you're asked about correlation and relationships between two variables and how you would structure your answer to those questions. So imagine, say for example here, this temperature, imagine it's for the temperature outside, and up the side sales maybe represents the sales of ice cream at a shop near the beach, something like that. Okay, so have a think about how you would answer parts A and B. Okay, the main things we're looking for here then is when you're asked to state the type of correlation, you want whether it's positive or negative or no correlation, and if it's positive or negative, say whether it's strong or weak. Now this example here, if I draw a line of best fit on, you don't have to, but it helps us see that the correlation here is pretty strong and the gradient is positive, so we just say that this is strong positive correlation. When it asks us to interpret the relationship, we want to talk about the variables that are involved. So try and think of an answer in context when it says describe the relationship. So what we can see is, as we've got positive correlation here, as the temperature increases, the sales also tend to increase. So we could just say that as temperature increases, sales tend to increase. So when it's talking about correlation, we should be using strong, weak, positive, negative, or no correlation. And when it's talking about relationship, be sure to include a context. Next, I want to think about dependent and independent variables. Okay, so as you can see from what it says down here, if you notice that one variable is dependent on the other, it depends on the way round we could say it. You could say the sales of ice cream depend on the temperature that it is outside. That makes sense. But if you said the temperature outside depends on the sale of the ice cream, it kind of doesn't make as much sense that way. Now it's quite obvious with this one, it's not always so obvious as this, but what we can do, the variable we put on the x-axis, we call that the independent variable, and the one on the y-axis we call the dependent variable, because the sales depends on the temperature, not the other way around. Okay, so independent variable goes on your x-axis, dependent variable goes on your y-axis. Right, a little activity for you to have 5 minutes to have a go at here. on slide 7 and 8 of the PowerPoint, I've put 8 graphs, and I'd like you to have a go at writing down what you think the correlation is in each of these diagrams. Some of them are straightforward, some of them are a bit more debatable, particularly about whether it's strong or weak, and we'll deal with that more later in the lesson. Some of them you might think, well, it looks like there's correlation, but is there? When we say correlation in this sense, we're thinking about linear correlation. So maybe think, could I draw a line of best fit for this data, and how close would the points be to it? So if you want to reveal the answers, you just have to click on these parts here. If you've got the PowerPoint open, feel free to go through it at your own pace. If not, I'll leave these 4 on the board for a couple of minutes, and then I'll skip to the next slide and I'll leave that up for a couple of minutes as well. Okay, off you go. Okay, let's have a look at some answers then for those of you that haven't seen them. So the first of all, we've got strong positive correlation. I think most people would agree with that. There's one outlier here though, which makes it maybe look a bit weaker. We'll talk about outliers later in the lesson. B, we've got strong negative correlation. And then C and D, we've got weak positive and weak negative correlation. Now, in my opinion, C and D are a little bit debatable. I don't think that these are quite weak. They're examples from the textbook that we use. The reason that I've left them in though and not used an obviously weak one is that I want people to see that sometimes it's quite subjective about whether you call a correlation stronger and weak. And that's one of the things that we're going to address in this lesson. Is there a better way of describing correlation than strong or weak, so that we're being a bit more objective about it? The next four then. So this one we've got no correlation in E. F, there's clearly some kind of relationship, but there's no linear correlation in here. It looks like we've got two separate sets of data. G, we've got perfect negative correlation. Now you might not have got the word perfect in there yet. If we have a correlation that is literally just a straight line and all the points fit perfectly on that straight line, we'd say we've got perfect negative or perfect positive correlation. And these two here, we've got two separate groups, each with each individual group we could say has strong positive correlation, but we can see overall there's two separate groups in the data, so that's something that can happen as well. Okay, so let's now address what can we do to have a more precise measure of how correlated two variables are. We're going to introduce something called the correlation coefficient. We use the letter R to represent this, and it's a number between -1 and 1. And that represents how strong is the correlation between these two variables. Now, there's a more precise name for this correlation coefficient, and that is the Pearson product moment correlation coefficient. A bit of a mouthful, sometimes abbreviated to PMCC. But we're just going to call it the correlation coefficient most of the time this lesson. Okay, so here is how the correlation coefficient works. It can take any value between -1 and 1. If we're at -1, that would be perfect negative correlation. And then as we go up, we'd get less correlation until we reach 0, which would be no correlation. And then if we get positive values, they're indicating positive correlation. And the closer we get to 1, the better, the stronger that positive correlation is. So R equals 1 would be perfect positive correlation. So we can have any value between -1 and 1. So these examples here, you don't have to write anything down. These are just some diagrams to illustrate what do these different values of correlation looks like. So top left, we've got quite low correlation, 0.3. You can kind of get a picture of what does R equals 0.30 look like. And then we've got increasing values as we go to the right along the top row until we get to R is 1, which is perfect correlation. And then at the bottom, we've just got an extra example with negative correlation. As you can see here, on R equals -0.9, 0.9 is pretty, -0.9 is pretty strong negative correlation, and yet if you think back to those diagrams we saw earlier, it's not much different to those. So by using numerical values, we can get a much more precise idea about whether there actually is correlation there. So a couple of extra caveats though to deal with. Just because you get a value of R that is small, as in close to 0, it doesn't necessarily mean that there's no relationship between the two variables. It's just that there's no linear relationship or linear correlation. So we could have correlation like this in the shape of a parabola. We could have a relationship like this in the shape of a parabola. We can see quite clearly from these points there is a relationship. But if you calculated the correlation coefficient, you wouldn't get a very high value. You might even get a 0 for this one. Another case where it doesn't quite work properly is when you've got two sets of data within one, kind of two separate strands to it. If you look at the graph here on the right, this would have quite a low, it would have a positive correlation coefficient because you can clearly see there is correlation. If you analysed any of these individual lines on their own, they would have very high correlation. But the value of R cannot distinguish between those two things. So again, for the value of this, you might not get a big value of R. Doesn't mean there isn't strong correlation in there if you think of it as two separate data sets. And what this allows us to see is you've got two ways of analysing your data here, and it's often useful to have both. The correlation coefficient may show you that there is some strong correlation or weak correlation there, but if you look at the scatter graph at the same time, you might see something that you would miss just by using the correlation coefficient alone. Okay, quick example for you to have a think about then. I'll do the answer in 1 minute. Have a look at these four graphs and decide which one do you think has a correlation coefficient of minus 0.94. You don't need to write anything down for it, but just make sure you've got a reason for ruling out the three that it's not, so that you know the one it is. Okay, so 1 minute to have a go at that then. Okay, just before we do the answers then, I think it's worth pointing out you're not expected to be able to say with any certainty what the value of the correlation coefficient would be by eye just looking at a diagram. So you wouldn't be expected to look at A and tell me with any precision what the correlation coefficient is for this. But by looking at these diagrams, there's only one that actually makes sense to be the answer. So if we look through them, graph A has positive correlation, so that's clearly not going to be minus 0.94. Graph B has no correlation or very close to no correlation, so that can't be it. Graph C, looking good. It's got negative correlation, looks pretty strong. Could be that one. Graph D, all of the points are in a perfect straight line, so that would have a correlation coefficient of -1. So the answer then would have to be graph C. So by a process of elimination, we can arrive at the one that it is. Right, quick activity for you to have a go at now. Ideally, if you've printed off the activity for this, it's better to have it in front of you on paper. If you can't, we understand that a lot of people may not be able to print it off, so you still will be able to do it. If you click on the link in the PowerPoint or go to the week 26 page, find the correlation matching activity. There's only the questions there aren't the solutions. I'll display the solutions on the board in a minute. If you click that file, you can open it up, and it's 2 pages that look like this. Okay, I apologise if these dots don't come up too well on the screen. I don't know what size screens people are using. So the idea is, for each correlation coefficient over here, there is a matching graph from 1 to 10. What I would like you to do is match up the correlation coefficients with the graphs. So you might write, for example, 1 equals whichever one it is, 2 equals that. So the only thing you really need to actually write down are the number and the correlation coefficient next to it. Okay, so I'm going to give people about 10 minutes to have a go at that. I'll leave these on the board for that 10 minutes so that anybody that's not got access to it can still use it. But if you can, you're probably best off loading it up on a screen or printing it off rather than trying to do it from this video. Okay, let's have a look at some answers then. One thing you might see to the answers to this is that it's not easy, and it's not all clear cut in some cases which one is which. So don't worry too much if you get any of these wrong. You're not expected to be able to maybe do some of these to the level of detail that are on this sheet. So for example, the first 4 here are the ones that are negative correlation, so you can check those. Now you should have at least the first 3, you should be able to spot that they are negative correlation. This one looks quite low. This one is negative correlation. It's not that obvious. Maybe this point at the top here is kind of indicating that, but that could maybe be an outlier. So in the exam you wouldn't necessarily be able to say what the correlation of this is, other than that it was very small. The same with these, it may not be obvious which one is which between 6 and 8, but you should at least have those the right way, not necessarily the right way round, but those 2 matched up with the top 2 here. Okay, then we move on to the positive correlation ones. I'll see if I can fit them all on the screen at the same time. Again, question 1 here, this one that's got very small positive correlation, you would not be expected to, with any certainty, to be able to say that number 1 was positive correlation and number 4 was negative correlation. But what you should be able to say is that they both have very small correlation, or no correlation almost. Okay, so if you've got number 1 and number 4 the wrong way around, doesn't really matter at all. You don't need to be able to spot that, but you should have 1 and 4 as the ones that have got the lowest correlation. You should be able to spot it to that level of detail. Okay, the rest of them are here. I mean, some of them you should definitely really be getting right. So for example, question 7, it should be quite obvious that that is the strongest positive correlation. So that should be the largest value of R, closest to 1. Okay, I'll leave them up for another couple of seconds and then we'll move on. Right, if you did have any questions about any of these, how to match them up, please do get in touch by email. It's andy.parker@bilborough.ac.uk. Maybe when we're doing the next activity, I'll have a chance to answer some questions. Okay, so next bit we're going to be looking at is correlation and causation. So 2 variables will have a causal relationship. It means one causes the other if a change in one variable directly affects a change in the other one. But just because 2 variables have maybe a high degree of correlation, that does not imply necessarily that one causes the other. And that is a common mistake that people make in everyday life, in mistaking correlation for causation. So here is a typical example. We've got a scatter graph here, and a newspaper publishes an article about this data that compares the hours children spend on a computer and their reading score. And if you calculated the correlation coefficient for this sample, you'd find that it was minus 0.36. So that is indicating that there is some degree of weak correlation, negative correlation, between the hours spent watching a screen and the reading score that 7-year-olds got in a test. Now the newspaper claims that there is a cause here. It says that screen time negatively affects reading scores. Now that may be true, but we've got to have, we'll do that when we're commenting on this claim. So there is definitely a negative correlation. So there is some kind of relationship between screen time and reading. Just because we know that doesn't give us enough information to say that one causes the other. It might do, or there might be factors that we've not considered that are linking the 2 things together that cause it. We just don't know. So if we were going to answer this question, we would, first of all, we'd say that there is correlation. We may mention that it's negative, and there is a relationship between the 2. We could even state what that relationship is. As screen time increases, reading scores tend to decrease. But what we can't do is say that one causes the other. This is a very typical exam question. They'll ask you whether one thing causes the other, and the answer is almost always no. Okay, now you wouldn't need to write an answer that is this wording. This is a bit longer just to explain things in a bit more detail. The key thing that we need is here we've got an explanation of the relationship between the 2 things, but we need to make sure that in the context of the question we say that just because there's correlation, it does not mean that one thing causes the other. Okay, just to illustrate the fact of how ridiculous sometimes trying to imply a cause just because two things are correlated, I've just got a few little pictures you might want to have a read of. Okay, so in all of these graphs, there is some kind of relationship between the two things. But it would be ridiculous in any of the cases we've just looked at to say that one thing causes the other. Global warming did not cause a decrease in pirates, that we know of. And so be very careful when you're analysing data to assume that something is caused just because you see correlation, however high the correlation is. Okay, we're going to move on to lines of best fit, something you should hopefully be broadly familiar with, but we're going to examine it in more detail at A level. So, you could, if there is correlation, you can generally draw a line of best fit onto your scatter graph. We could also refer to this line as a regression line. Okay, now we need to be able to draw the lines of best fit and we need to be able to interpret them. But what we don't need to be able to do on our course is calculate the line of best fit mathematically. That's a little bit beyond the scope of the course, but it is possible, and we'll talk about how you might go about doing that just so that you can see that it's possible. Okay, so let's imagine that I recorded the marks of some people in a test, and I also asked them to fill in a survey with how much time they spent revising for that test, and these are the 7 results that I got for that. Now, clearly there is a line of best fit we could draw. There's a positive correlation in there that we could draw on that. But how do we get the best line of best fit, the best regression line for this graph? Okay, so one method you could do, and you don't need to know the specifics of this, we're just going to give you an idea of how it works. If that's a straight line, then you could find the equation of that straight line. It would be of the form y equals mx plus c. This one here, for example, could be 20 plus 3x. And if you draw that line of best fit, you could measure what is the vertical distance between each of your points and the line of best fit. Now, the better the line of best fit, the smaller those distances overall would be, or the average distance would be as small as possible. So, what we could do with is a method for finding the average distance and making that as small as possible. Okay, and that's the idea of a method called least squares regression lines. So, because some of the values will be negative because they're below the line, some will be positive, what we would do is we would square all of the distances. Then we'd do some maths that's beyond the scope of the course, and we would attempt to minimise the distance each one of those is from the line. Okay, now, we're not required to do that, but we are required to use lines of best fit as equations and understand what the values in here mean. So what does the gradient mean here, and what does the intercept in terms of the question that we're being asked, in terms of, say, time spent revising an exam mark. Okay, so don't worry about the method behind how to do that. It is interesting if you want to look it up. It used to be on the old Statistics 1 module in the old specification, so there's plenty of stuff out there on it. We're just going to have a look at what does this line here mean. Okay, so we've got a new scatter graph here. We've got distance travelled in miles and the time taken for a random selection of car journeys. And somebody has already drawn a line of best fit onto this graph. Okay, and if we could use a method to find out what the equation of that line of best fit is here. And we've got 0.7x plus 0.9. So that is the equation of the line of best fit that's been drawn here. And we're going to have a look at what does the 0.7 mean and what does the 9 mean. Well, the 0.7 represents the gradient of this line. That's how steep it is. So essentially another way of saying that is for every 1 mile we go across, how many minutes do we go up? Well, the answer would be 0.7. So the meaning of this 0.7 in here is how many minutes it would take to travel an extra mile according to the line of best fit. Okay, so it's a prediction of in 1 mile how much extra time would that take. Now the 9 here, if we were to extend this line until it touched the axis over here, it would touch the axis at 9, and that would be indicating that a journey of 0 miles would take 9 minutes. Okay, that's what the 9 means. According to this model, a journey of 0 miles would take 9 minutes. Okay, so that's the meaning of the two things, but it highlights something else that's really important when we want to use this line of best fit. And that is, we can only use the line of best fit to predict values that are within the range or very close to the range of values that we already have. So we'd be predicting, if we extended this line, that a journey of 0 miles would take 9 minutes, which is clearly ridiculous. And that is one of so the reason there is that we cannot predict values that are outside the region that all our data lies in. Just in the same way we couldn't predict how long a journey of 20 miles would take, because we're looking at data way outside of the region we've got, and that is called extrapolating. Now, for values close to or just outside, you tend to be okay, but the further away you get from the data you captured, the more danger you've got of wrongly predicting something. Okay, so I've got one for you guys to have a go at now. Okay, here is a graph. It's the same one I had on the board a minute ago. Have a think, see if you can write down an answer just so that you know you've clearly understood it. What does the gradient of 3 represent in context, and what does the y-intercept of 20 represent? So relative to what we've got written on the axes. So a couple of minutes to have a go at writing down your answer for that. Okay, answers to this one then. So for the first one, we'll be looking at if we go 1 hour across, so if we spend an extra hour revising, how many extra marks would we expect to gain by doing that? So that's what the gradient represents. For every hour, how many extra marks might you expect? And for the intercept, well, 20 would be over here when you've spent 0 hours revising. Essentially, what score would we expect a person who did no revision overall to get? In this case, it would be 20. Now, this value here is a little bit outside of the region that our data is in. So we're not saying that you could not predict that value there as being 20, but you should use caution when you're using values outside of the region you've got. So, a little bit of a summary then before I leave you to have a go at a few questions. So, when we've got our line of regression or line of best fit, we can use it to predict other values, but sometimes we need to be cautious about when we do that. So we should only first of all use it to predict dependent variables, the ones on the y-axis, and we should only use the line of best fit to predict things that are within the range of the data we've got. If we go outside of that region, we need to use a little bit more caution about the answer we get. And a little bit of terminology, we've already talked about extrapolating. That's when you try and predict a value that's outside the range of your data. If you try and estimate one that's inside the range, you could call that interpolating. Okay, right, I'd like to have a go at a few textbook questions now. So it's exercise 20D. I want you to do question 3 and then questions 5 to 10. Now, you might not get all of these done. Okay, I'm going to say about 20 minutes or so, maybe 25 to have a go at them. And then towards the end of the lesson, we're going to come back and we're going to have a look at some cleaning data and some outliers. So we're going to start the next topic towards the end of this lesson. And we've got 3 topics to cover over the next 2 lessons. Okay, so I'm going to start the timer at 20 minutes. What I'll do around 20 minutes, I'd like people to give me some feedback about how far they've got. If it turns out that loads of people haven't got very far, then we might spend a little bit more time on it and it'll just push us back a little bit. So please do give me some feedback after about 20 minutes. How far have you got with these questions? So this is from the textbook that we normally use, the Cambridge Elevate one. What I will do towards the end, I'll display, well, in fact, if you haven't got access to the textbook, let me know and I'll try and get you a copy of the pages that you need in a different way. Okay, but hopefully most people will be able to access the questions and the answers from the textbook. Okay, off you go. Okay, we'll soon be coming up to having spent about 20 minutes on this. I'm not sure whether that'll be enough time because I don't know how long it's taking people to log into textbooks and things like that. So what will be really helpful is if a large enough sample of people just send me a quick email and say, what point have you got up to? I'm not expecting everybody to get all of the questions done, but it would be useful to know how far along we've got. If most people have got to a suitable point, we'll move on straight away and look at some outliers and cleaning data. Otherwise, I might give you an extra 5 minutes or so. Okay, so I'll wait until I've got a few emails and then we'll make a decision. Okay, thank you to everybody who got in touch. Really appreciated there. The vast majority of people that have got in touch with me have said that they're right at the end. They've either finished or they're on question 9 or 10. So I'm just going to give you another couple of minutes while I set up the next PowerPoint, and then we'll move on to some outliers and cleaning data then. Okay, so next topic then. Links in very nicely with the stuff we've just done on correlation, which is why we're doing them both together. So when we talk about cleaning data, we're talking about when you collect data in the real world, there's often some problems with it. You get errors from measurement, you might have some data that's missing, and you get some extreme values that might be valid, or there might be things that you need to consider getting rid of. And we're going to look at how do we deal with those outlier values in this lesson. Okay, so if we just leave them in, they distort our results, and that can cause us problems when we come to look at patterns and trends in our data like we've just been doing. So first of all, we'll start with a definition of an outlier. We're going to say that an outlier is any data point that is inconsistent or doesn't fit with the rest of the data. And we have to accept, to start off with, that there is no one fixed universal definition of what we mean by an outlier. Okay, one person's outlier might not be another person's outlier. Some of them are obvious. Some of them you might argue with people and say, well, no, I think that value is not an outlier. Okay, so when we've decided that something is an outlier, we might decide to leave it in the data if we've got a reason to, or we might decide to remove it, and we'll look at when might you do that as well. Okay, so the first way we might spot an outlier is we might have the data represented graphically like a scatter diagram, and we can see quite clearly in this one, there's a point down at the bottom here which doesn't fit with the rest of the data. That's a nice obvious example of an outlier. Okay, so sometimes we can just look at the data graphically and we can spot outliers that way. Okay, there's other ways of defining outliers though. In order to do so, we're just going to have a look at some terminology from GCSE and earlier in the A-level course that you should hopefully be familiar with so far. So I've got a diagram of a box and whisker plot on the screen at the moment. What I would like you to do, I'll give you 1 minute. Can you just see if you can label the little parts of it? What do those arrows represent? What they're pointing to? There's 5 different parts of the box plot that we should be able to know. And then underneath, can you write down a simple calculation that would result in the interquartile range? Okay, so label up the box plot. It doesn't have to be a work of art, just a quick sketch, and then write down how you would calculate the interquartile range. Okay, so just a minute to do that then. Okay, so right down at the left hand side here then we should have the smallest value or the least value. The next line, the start of the box, that should be your lower quartile. The vertical line in the middle is your median. The end of the box is the upper quartile. And the final one over here, that should be your largest value. And to calculate the interquartile range, we do the upper quartile minus the lower quartile. Okay, so we're going to use this definition, we're going to use these values here in our first definition of an outlier. Okay, so our first method that we may use to identify an outlier is we could say that it's any data point more than 1.5 interquartile ranges away from the nearest quartile. Now that, well, bit of a mouthful, it might become a bit clearer from the diagram. So on the diagram here, I've labelled up the interquartile range. Okay, now if I move that interquartile range to the right so that it starts where the upper quartile is. Okay, actually this diagram is not quite right. I need to edit this. It's not the interquartile range in this direction. It's 1.5 times the interquartile range. Okay, so a bit of a mistake in the PowerPoint there. So if I start at the upper quartile, I know what that value is, and I add on to that 1.5 times the interquartile range, anything that comes past that point would be defined as an outlier. Let's have a look at the other end. If we went the other way and again did 1.5 times the interquartile range, anything that was in here would be an outlier. However, 1.5 times the interquartile range at the lower end actually takes us past the lower value. And so in this case, there are no outliers at the lower end. There's only the outlier at the upper end. Okay, let's see what that looks like in an example then. So imagine we've got a group of people and we asked them to do as many keepy-uppies with a football as they could. And we drew the results for some reason on a box and whisker plot. And then we want to determine, is there anybody who is an outlier, maybe super brilliant or super rubbish at doing keepy-uppies. Okay, so here is our box plot. We'll put that at the top of the screen. First of all, we'd need to calculate the lower, we'll just read off the lower quartile and the upper quartile. So we've got 9 and 17 for that. And those two values would allow us to find the interquartile range. So 17 minus 9 is 8. Okay, then, first of all, we'll look at the top end. Are there any outliers above the median? Okay. Oh, no, I've done it the other way around. Sorry. Starting at the bottom end. So if we start with the lower quartile of 9, and we subtract from that in this direction 1.5 times the interquartile range, the calculation we'll be doing is 9 minus 1.5 times 8. That's going to get us -3. Now, we're not going to have -3 keepy-uppies, so there is nobody at the lower end because the lowest value was 2, and this is below there. Okay, so there's no outliers at the lower end. However, if we do the calculation at the other end, start at the upper quartile, add on 1.5 times the interquartile range, in this case we get 17 plus 12, which gives us 29. Okay, so anything past 29, which is here, would be an outlier. Now, we don't know from the data we've got how many values there are that are outliers, but we do certainly know that there would be one outlier, because we know that the maximum value is 32. So we know that in this set of data there is at least one value which is an outlier. Okay, so the largest value 32, which is an outlier. There might be more, we don't have enough information to say. Okay, so that's our first method of defining an outlier. We've got another method that we can use as well, which might be more useful depending on the form that the data is given to us in. So the second definition is that an outlier is any data point more than 2 standard deviations away from the mean. So I've got my data here. Let's imagine that x bar represents the mean. This is the lowest value on the left here. This is the greatest value on the right here. If we measured how far 2 standard deviations was, so 2 times the standard deviation in either side, and marked that on our line, anything outside of that region would be an outlier. Okay. So let's use that in an example. Here we go. We've got the wages of some employees given in a table. So we've got 18 employers earning £10,000. We've got 14 employees earning £16,000, 4 earning £20,000, and then 1, obviously the boss, earning £145,000. And we're going to determine if 145,000 is an outlier. It certainly looks like it might be. Okay, so we need to calculate the mean and standard deviation for this table. We can do that just on our calculator. So I'll go through the steps to remind you of how you might go about doing this. So if we're on the main menu of our calculator, we would go into stats mode. I've already put the values in here because I made the question up the other day. We've got 10, 16, 20 and 145. So the x values essentially are going to be in the first column, and the second column is the frequency column. Okay, and then I'm going to press F2, which is calc. Now, you might need to do this next bit, you might not. If we go into settings here, set F6, you need to make sure that your X list is set as list 1 and that your frequency is set as list 2. It might be that this doesn't say list 2, it says just the value 1, which would be if we had a list of values where each one occurred once. But we've got a frequency table, so make sure that's list 2. Go back out of that. Okay, I want a 1 variable calculation, so it's F1, and here are my values. So my mean x bar is 17, and my standard deviation sigma is 21.6, and so on. Use more decimal places than you'll need for that. Okay, so we've got our mean of 17, standard deviation 21.6. Okay, so the calculation we're going to do to determine if it's an outlier is, well, there's not going to be any values. If we do x bar, the calculation we do for outlier, let me just write it down rather than mumbling. So x bar plus or minus 2 sigma. Now, x bar minus 2 sigma, we can see without doing the calculation, will be a bit pointless because it's going to be negative. Nobody's earning negative amounts of money. So we're going to do x bar plus 2 sigma. So 17 plus 21.6, and we'll get a value for that. Now, to save myself the trouble, I've already done the calculation. It's here. You get 60.3, which is just over £60,000. So at this company, anybody earning more than 60.3 thousand is going to be an outlier. So in this case, 145,000 is most definitely an outlier. Okay, so that's another way of calculating outliers. Okay, final bit of a consideration here then is, what do we do when we've found an outlier? Do we leave it in the data or not? Well, it's kind of, you have to take the context of the data here. If it's obviously an error, then get rid of it. You don't want errors in your data. It's just going to make it more noisy. Okay. You might also want to consider the context of the data. Now, the 145,000 that we just saw, that's probably not an error. So you're not removing it because it's an error. But if you wanted to know, if you wanted to really crunch the data about that company, it's going to kind of really shift the wages. So if I just go back, for example, to this, if I was to work out the mean wage of this company, it would come out much higher than you might expect, because the 145,000 is going to pull the average wage up. And you could then be quite misleading about the data if you wanted to. You could say that the average wage of this at this company is higher than it actually is, because you've included the wage of the CEO, when really, if you're talking about the average wage of somebody at a company, we'd probably exclude that 145,000 to get a fairer value. Okay. If you find that there are a number of outliers in your data, it might actually be they're not outliers. If you remember earlier in the lesson when we were looking at some scatter graphs, there were a couple of examples where there were actually two sets of data within the scatter graph. And it wasn't actually that something was an outlier, it was just that there were two sets of data that we kind of considered to just be one. So don't just do the calculations. If you can, represent the data graphically. That might show you some things that you might not otherwise have seen. Okay, we're going to do a few questions on this now. We'll start with a few of them now. We've got 10 minutes left, so I'll be here for another 10 minutes if you want to ask any questions. And then at the beginning of Friday's lecture, I'll give you a bit more time to work on these questions. And obviously, if you do anything in between, then you can obviously ask me questions at the beginning of that lecture if there's anything you're not sure about. Okay, so it's quite a short topic this. There's only those two methods we really need to consider. You'll probably find that the questions are quite easy, but there might be the odd one that catches you out a little bit. If you really want a challenge, question 9 is quite a nice one to have a go at. There's some tough bits in that. Okay, so feel free to crack on with the questions. I've just had a couple of emails through. Somebody wants me to go through the calculator thing again, so I'm just going to do that. But if you already know how to do that, then feel free to just crack on with the questions for another 10 minutes or so. Okay, so I'll just go through the calculator thing again then. So starting from the beginning, when you're on the main menu, you want to go into stats mode, which is number 2. Okay, then I've already got these values in, but you might need to type them in for yourself. The first column in your frequency table is just the first values in the table. So I'll briefly just go back to the question we were on. So along here, these are the different values that the salary could take: 10,000, 16,000, 20,000, 145. So I'll put them in the first column. The second column, where we've got list 2 here, this is your frequency column. So how many times does each value occur? So £10,000, there are 18 employees that earn that amount. So the frequency value is 18. £16,000, there are 14 members of staff that earn that amount. So 14 goes in the frequency column, and so on. Okay, now the next bit I did was setting up my calculator. So I went into this part here that said calc. That's where I do all my calculations. What I need to do is I need to tell my calculator that the values in this column are essentially the values that I can get, the inputs, and the values in column 2 are the amount of times that each input occurs. So the value of 10 happens 18 times. So list 2 is essentially the frequency column in a frequency table. So I go into set over here by pressing F6. One variable X list, that will, unless you've messed your calculator up, if you reset it, that would go to list 1. But this second value here where it says list 2, if you've not done this before on your calculator, that will just say the number 1, just like this here. Okay, and that will essentially be saying each value in my list occurs once. But we don't want that. We want 10 the value of 10,000, we want that to occur 18 times. So we go into this one and we change this here. We press list, and then we change it to the second column, so we put list 2, and that will change that value there. And that is telling our calculator that the second column is a frequency column. Then we go back out of that, and then whenever we're doing these calculations, we've only got one variable, and that's the wages. The other column is not a variable, it's the number of times that it occurs. And then we press one variable, and you get all of these values in here. Now, if you've not seen these before, because you've not done this, I'll just go through them. X bar represents the mean. Okay, sigma x here, this one, is what you would get if you added up all of the values. So this 629, to get that calculation, you would do 10 plus 10 plus 10 plus 10 plus 10 18 times, plus 16 plus 16 plus 16 plus 16 14 times, plus 20 plus 20 plus 20 plus 20, plus 145. That would give you that value here. Okay, these values here, sigma x and sigma x squared, are useful if you're calculating the standard deviation by hand, which is something you should hopefully have covered earlier in the course. Sigma x squared, that represents if I take each value, like 10, and I square it and then add them together. So 10 squared is 100. So I'll be doing 100 plus 100 plus 100 plus 100 18 times, plus 16 squared 14 times, plus 20 squared 4 times, and so on. Okay, sigma x is your standard deviation, the one we deal with in the course. Sx is another measure of standard deviation that you won't see unless you do further maths. N is the number of items, so if I added up the frequency column, there's 37 items, 37 employees in this case. Okay, these values are useful for maybe for other questions we're doing. Minimum value, lower quartile, median, upper quartile. So those could be quite Q1 and Q3 if you wanted to calculate the interquartile range of your data. Helps you out there. Maximum value, mod is the mode. What's the most common one? Well, it's 10 in this case. Okay, and that's all the ones that we're really going to be interested in. Okay, so I hope that's helpful in showing you what you can do on your calculator there. Okay, so we've got another 5 minutes left. If anybody's got any questions in the next 5 minutes, please let me know. Then we'll carry on with the questions at the beginning of the next lecture, or you can carry on with them in your own time, just finishing them whenever. It's up to you. Okay, that's the end of today's lecture then. Thank you everybody for watching. If you come up with any questions on either set of problems we've done today that you want me to address at the beginning of next lecture, then feel free to email me. If it's a simple one, I'll just email you straight back and answer it. If it requires a bit more detailed explanation, then I'll just leave it to the beginning of the next lecture. Okay, have a nice few days.